Okay, so this chapter is chapter 19, Enolate Anions and Enamines. So what an enolate anion is when we have like something that looks like an enol, like this over here. But an ion is when we have a charge, like a negative charge, onto either the oxygen or this or carbon over here, and they're resonance structures of each other. So to get that, we deprotonate the alpha hydrogen of any carbonyl, like aldehyde, ketone, or ester. In this case, we have an aldehyde, so we have a base that deprotonates this alpha hydrogen to give us this enolate ion over here. And this negative charge um, is our nucleophile on this carbon over here. And the reason why is because which structure is more stable? Is this structure more stable, or is this structure more stable?
Is it the first one?
The first one, which one is more electronegative, carbon or oxygen?
Oh, oxygen's more like.
Yeah, oxygen is more electronegative, so it's better able to hold its negative charge. So this one is more stable. That means it's less reactive. And since this is less stable, it's more reactive. That which is why this is the nucleophile. This carbon here is the nucleophile. Since it's more reactive and less stable. Let's see. And these enolate anion nucleophiles can undergo SN2 reactions by acting as a nucleophile and attacking another electrophile, like a like a alkyl halide. Where here where this is the electrophile, where this nucleophile attacks this electrophile SN2 reaction. And I started the attacking carbon and dotted the carbon being attacked, and then kicked out the leaving group. So this is the new bond right here between the starred and dotted carbon. And we see the starred carbon is attached to two R groups, 1, 2, and the blue dot carbon is attached to one R prime group right here. And the Br minus got kicked out as a leaving group. And this is an Aldol condensation reaction because our enolate anion here is attacking another carbonyl, which is an aldehyde over here. And I started the carbon being attacked and dotted the carbon. I started the attacking carbon and dotted the carbon being attacked and made a new bond between that. And then I did the same trick. I drew what's attached to both the starred and dotted carbon. Do you have any questions on this slide?
No.
Okay. Aldol reaction. Do you just want to go over like the slides that you're confused on? Because I think you already understand the Aldol reaction, or you want to go over like every slide.
I feel okay on the Aldol reaction. I've definitely been doing a lot more base catalytes than acid.
Yeah,
So
base catalyzed is the more common one, the more common version than the acid catalyzed.
Why?
That's because it's shorter, and also if you put acid into the mechanism, there could be other side reactions like SN1 reactions and stuff like that. Whereas base catalyzed Aldol reactions like ensure that you only go through the Aldol reaction. But
Okay.
it still works with acid catalyzed for Aldol reactions, but usually professors go over the base catalyzed version.
Yeah, I feel comfortable with aldols right now.
Okay, Aldol. Crossed Aldol, that's when you
Definitely.
have like two different carbonyls. Yeah. And these are like the carbonyls that does not have any alpha hydrogens. So these carbonyls here cannot be the nucleophile. They can only be the electrophile. And this is how you ensure that you avoid crossed Aldol reactions.
So usually the ones with alpha hydrogens will be the ones that attack those ones.
Yeah, the ones with alpha hydrogens would be the one that's the attacking. Yeah.
Okay,
And these ones are the ones that are going to be attacked because they have no alpha hydrogens.
got it.
Oh yeah, this is the one that you saw on Discord right here.
Yes.
Yeah,
I
so this
will.
is intermolecular Aldol reaction right here, where we have two alpha positions that could be the nucleophile. So let's do alpha 1 first, and then let's do alpha 3 after that.
Mm.
Okay, so in alpha 1, let's say we deprotonated it with a hydroxide right here, giving us this enolate anion. And this resonance structure right here, you don't have to draw in the mechanism, but some professors want you to draw it for full credit. So I did it just in case, but I don't know if your professor requires this resonance structure.
I think so.
Yeah, so I would draw it for full credit, and then I redrew.
Oops.
I redrew this structure here onto the second step, where you know how usually we attack a different carbonyl. That's an intermolecular reaction. This time it's gonna attack a carbonyl on the same molecule, which is an intramolecular reaction. So I attacked a carbonyl that is like 7 carbons away, because I numbered this attacking carbon 1, and then I went all the way to the carbon being attacked, which is 7. 1, 2, 3, 4, 5, 6, 7, which we formed a 7-membered ring. And then I attached whatever is attached to which carbons. At carbon 2, that I saw that there's a carbonyl group there. At carbon 1, there are only hydrogens there. And this is the new bond right here between carbon 1 and carbon 7, because before there were no bonds between carbons 1 and 7, but now there's a new bond there. And then at carbon 7, there's a methyl group, and there used to be a double bonded to oxygen, but now it got kicked up onto a single bond to oxygen with the negative charge right there. And then this negatively charged oxygen would get protonated by a water molecule, reforming our base catalyst over here. And then our dehydration step is when we deprotonate the alpha hydrogen between these two alcohol oxygens, making the double bond there and kicking out the OH group right here.
Mm-hmm.
And you see how here we form a 7-membered ring. This is less stable than the 5 or 6-membered ring, which is why this is not formed. Instead, if we take the alpha 3 hydrogen and we do the exact same mechanism, we form a 5-membered ring, which is more stable, and this is the major product here that will be formed.
Can you highlight the new bond form in step 3?
Yeah, the new bond form right here. Let's see. So in step 3, this one right here.
Mm-hmm.
Yeah. So in step 3, the hydroxide deprotonates the alpha hydrogen between this oxygen and this oxygen and makes a double bond right here. This is the new bond that forms in step 3, the double bond, and it kicks out the alcohol group.
Can you show me in the other number 3?
The number 3, let's see.
Because I don't understand how it makes a new bond with each other. Because like I'm
this number 3 right here.
I'm
yeah.
always missing that one bond, so I'm always one short.
Oh yeah, this double bond right here.
Yeah. No, before that, like when you combine 1 and 7.
Oh, like making the ring.
Yes.
Yeah. So we see here, this is our nucleophile here, the enolate anion. Since this is our nucleophile, we look for our electrophile. In this case, our electrophile is in the same molecule as the nucleophile, which this is the blue dotted carbon, the electrophile over here. And since they're in the same molecule, this is the intermolecular reaction where this nucleophile attacks the electrophile at the same molecule, and it kicks up the carbonyl bond onto the oxygen. And I numbered it 1, 2, 3, 4, 5, 6, 7. So I know that I made a 7-membered ring. So when I draw the product, what I draw first is a 7-membered ring. I don't draw any other groups first. I just draw a 7-membered ring first, and then I number it 1 to 7. And then you know how before there was no bond between 1 and 7. There's only a bond between like 1 and 2, 2 and 3, 3 and 4, 4 and 5, 5 and 6, and 6 and 7. This right here is the new bond between that we made between 1 and 7.
And that's like the same in like glycine condensation too.
Yeah,
right?
that's the same in the regular glycine condensation. But in that case, we have 2 different molecules. We don't form a ring. I'll show you an example of that.
I think it might be later.
Oh, they went over. Oh yeah, that was an intramolecular Aldol reaction, not Glycine.
I'll wait till
Yeah,
we get there.
yeah, Glycine also has the intramolecular Glycine condensation. Yeah. Mhm. Yeah. And the product of an aldol reaction or dehydration will always be this enone right here, an alkene next to a carbonyl. We see an alkene next to carbonyl here. We also see an alkene next to carbonyl here. Yeah. Okay, and now let's move on to the Claisen condensation. For Claisen condensation, we use esters as the nucleophile, and the product of Claisen condensations will be a beta keto ester. So what a beta keto ester is when you have an ester over here, beta to this ester, you have a carbonyl, which we call ketone. So this is called a beta, because the beta carbon, we have a ketone to the ester, beta keto ester. And here's the mechanism for Claisen condensation. This is the reaction, the top part over here, and below that, I drew out the mechanism. So in the reaction, we have two esters and two steps, where the first step is ethoxide. The second step is water and acid. And we form this beta keto ester because we have an ester right here, and beta to that, there's a ketone right there. So in the first step of this Claisen condensation, we deprotonate the alpha hydrogen of this ester and make this nucleophilic enolate anion over here. And after we form the enolate anion in the first step, we move on to the second step, where we take that nucleophile enolate anion and attack another ester, since we're given two esters here. So I starred the attacking carbon and I dotted the carbon being attacked. And then I first, when I drew out this product, I first drew out the enolate anion, which is this structure over here with the starred carbon. And then this is the new bond right here, the new bond between the starred and dotted carbon, which came from this arrow right here. So this is a new bond, this is the dotted carbon. And then I drew what is attached to the blue dotted carbon, which was one methyl group, one ethoxide group right here with the oxygen bonded to two carbons. And then there used to be a double bond to oxygen, but since we kicked it up there, we have only one bond to a negatively charged oxygen. And then from here, we reform our carbonyl by moving one of the lone pairs of this oxygen down and kicking out this ethoxide group. And this ethoxide group, you know how it's a bad leaving group?
Yes.
Yeah, so since it's a bad leaving group right here, it needs to come back and take its vengeance and attack the alpha hydrogen between these two oxygens over here. So after that, it deprotonates this alpha hydrogen, which gives that alpha carbon a negative charge. And then at the very last step, we just protonate that with acid, which is the second step over here.
Okay, I think my problem was just directly connecting the red and the blue instead of making that bond. So instead I would attach the oxygen and the OET to the
Yeah.
red dot instead of adding the new line. So that makes a lot more sense.
Yeah, like I would star the attacking carbon, dot the carbon being attacked, and then make the new bond between them over
Mhm.
here, which is this one. Yeah.
Why can't you protonate the ethoxide right away? Like
Oh,
you don't need deprotonate and then protonate that.
ethoxide, like this one over here.
Yeah.
Yes, because this one we can't do that because this is originally a bad leaving group, this O stage 2, stage 3. So we were able to kick that out because it comes right back immediately to attack the hydrogen.
Yeah, but why can't you just
Oh,
protonate
like
that?
protonate this before we kick it out?
No, the ethoxide. Yeah, protonate that.
Oh yeah, because we're not in acidic conditions. We're still in this first step over here. And before we can add the second step of acid, it would be too fast for this to attack the alpha hydrogen, because this step happens right after it leaves. Like think of it as in like a super fast reaction. Like right after the bad leaving group leaves, it's super reactive because it's super unstable. So it will come back and take its vengeance and attack the alpha hydrogen immediately. Before you can add the second step of acid. And then after the alpha hydrogen gets deprotonated really quickly, and then you add the acid, then that deprotonated alpha carbon gets protonated and becomes neutral. And the Dieckmann condensation is basically an intramolecular Claisen condensation. It's the same thing, but the nucleophile and electrophile are in the same molecule. So the top here is the reaction, and we see that we formed a ring. And here's the mechanism over here. We have two esters still, but this time they're on the same molecule. We bring in our ethoxide, we deprotonate the alpha carbon, and that alpha carbon now has a negative charge, which is this enolate anion over here. Draw out the resonance structure for full credit, and then I redrew this resonance form over here, where we see that this alpha carbon is the nucleophile, and the other carbonyl carbon of the other ester is the electrophile. So this nucleophile here will attack the carbonyl carbon electrophile, and this forms a 1, 2, 3, 4, 5 membered ring. So what I do first to draw these types of products is I ignore the other groups and then I just draw out the base ring form. So I draw this cyclopentane over here, or this pentagon first. And then I number it 1, 2, 3, 4, 5. And then I draw what's attached to each carbon. At carbon 1, we see that we have this ester group attached to it. So I drew that ester group attached to carbon 1. At carbon 5, we have an ethoxide group attached to it. And there used to be a double bond to oxygen, but now it's a single bond to a negative oxygen. And then from there, we do the exact same steps as the previous mechanism. We reform the carbonyl, kick out the bad leaving group. The bad unstable leaving group comes back for its vengeance and deprotonates the alpha hydrogen right away. And then we bring in our second step of acid to neutralize that alpha carbon. And then we see here in our Claisen condensation reactions, our product is always a beta keto ester, because this is our ester over here, and beta to that is a ketone. Yeah.
So most of these condensations follow similar mechanisms.
Yeah, most of them do. They follow the same similar mechanism. For Claisen condensation, you start with an ester.
Mhm.
For aldol condensation, you start with a ketone or aldehyde.
And then, so for cross condensations, how do you know which one? So actually, no, cross condensation will be with either an aldehyde or ketone.
Yeah.
And
For cross Claisen condensation or cross aldol condensation, that's when you have multiple esters or multiple aldehyde and ketones that could be the nucleophile. So there could be more than one nucleophile, which will give you multiple products. So I'll show you an example of that over here.
Okay.
Wait, can you go back to Dieckmann really quick?
Yeah. So.
Oh, here we go.
So in that first step, when you're deprotonating the alpha hydrogen, why can't you just make a double bond and then move the double bond from the carbonyl onto the oxygen? Or is that only elimination?
This step over here.
Yeah.
Like why don't I make
Like,
this double bond right away?
Yeah, instead of making a carbanion.
Oh yeah, yeah, I could do that as well. Like when I attack this hydrogen, I could make a double bond there and kick the carbonyl onto that oxygen, and then that would give me this resonance form, which is the exact same thing as the first one. I just did the carbanion first because that explicitly shows the nucleophile, the attacking atom, which is this carbon over here. You could do it this way as well, but when you do it this way, make sure to draw the other resonance form with the carb anion as well. That's the same thing.
Wait, the attacking.
Atom is this carbon over here. So when you go do the double bond and kick the carbonyl up there, you're going to get this resonance form. Make sure to draw the other resonance form, which is this one over here, because this shows that this atom here is the attacking atom, this carbon, not this oxygen. And then for this step here, I just took this resonance form because it shows the nucleophile more clearly here. Does that
So,
make sense?
so Clayson is making a 6-membered ring.
It could be a 6 or 5-membered ring depending on how long the nucleophile is from the carbonyl. So in this case, this is a 5-membered ring because you see how here this nucleophile is 5 carbons away from this electrophile. 1, 2, 3, 4, 5. It would be a 6-membered ring if this ester was 1 carbon away. So it depends on the molecule.
Oh, so in the example you had earlier, so 5 and 6 is okay, but then 7 is unstable. So that's why
Yeah.
we don't make it.
Yeah, sure. Right here. This for Aldol condensation right here. We have multiple nucleophiles that we could choose from. It could be either be alpha 1 or alpha 3. I did both of them. But we see that alpha 1 is unstable because it forms a 7-membered ring. So the favored nucleophile would be from alpha 3 because it forms the more stable 5-membered ring right over here. And this is unstable, so we don't want to deprotonate this alpha 1. We want to deprotonate this alpha 3 as a nucleophile. And this is intramolecular Aldol condensation, not intramolecular Claisen condensation. Because we start with a ketone or aldehyde. We don't start with the ester. For Claisen, we start with an ester as the nucleophile.
What does Diekman start with?
Diekman is intramolecular Claisen condensation, so it also starts with
Ester.
ester, yeah. But the electrophile is also on the same side as the nucleophile. Okay.
I'm ready.
Okay, so for Claisen condensation, since we start with esters, we see that this ester cannot be the nucleophile because it has no alpha hydrogens. This alpha carbon here has no alpha hydrogens, which means that this ester here is a nucleophile because this alpha carbon here has alpha hydrogen. So typically our electrophile is in excess because once we make our nucleophile, it could attack itself or it could attack the electrophile. So we wanted to attack the electrophile, so we add it in excess here. And then the mechanism is the same as the other Claisen condensation we did, but just with different nucleophiles and electrophiles, where this starred carbon is the nucleophile after we deprotonate the alpha hydrogen, and this blue dot is the electrophile. And for problems 19.20, this is showing you a crossed Aldol condensation or reaction problem. They want you to draw all 6 possible Aldol products. So the way I do this without drawing the mechanism is a shortcut, is that I am going to figure out what my nucleophiles are first. So in this case, you see how here we have let's see. Let's see. 1, 2, 1, 2. Okay. 3 different nucleophiles. I'm going to do that 3 different nucleophiles now. Label it alpha 1, alpha 2, and alpha 3. The reason why I don't label this as a different nucleophile, because this nucleophile will be the exact same nucleophile as alpha 1. I labeled out the different alpha carbons here. So we have 3 different nucleophiles. Let's focus on alpha 1. Alpha 1. Okay, let's color code them. So alpha 1, I'm just going to deprotonate it right away. We have a enolate ion there, a negative charge on that carbon. This can react with itself like this and give us this product, or it could react with the other ketone, which would give us this product over here. So we see here this dotted carbon is bonded to the O- and 2 methyl groups for this first example. This dotted carbon is attached to O- and 1 methyl and 1 ethyl group. And then after they get protonated, this O- will have a hydrogen. So these are our 2 different products. We have 4 more. So let's look at alpha 2. So alpha 2, we have a negative charge on that alpha 2 carbon. It could react with itself, giving you let me draw the nucleophile on the left side, star that. New bond between the starred and dotted carbon. I dotted the wrong carbon. The dotted carbon would be this carbonyl carbon. And then I draw what's attached to the dotted carbon, which is a O-, ethyl, and methyl. And after it gets protonated, it becomes an alcohol. Or this alpha 2 can attack the other ketone that we have. Same process. New bond between the starred and dotted carbon. O-, which becomes an OH after it gets protonated, and 2 methyl groups. So those are our other 2 products. And let's look at alpha 3 now, where our negative charge is now on this alpha carbon. It could attack itself like this. And give you this is the new bond between the starred and dotted carbon. This will be OH. That dotted carbon is attached to an O-, which gets protonated to OH, ethyl group, and a methyl group. Or it could attack the other ketone here. Which gives you new bond between the starred and dotted carbon. This dotted carbon is attached to O-, which gets protonated to OH, and 2 methyl groups. So here are your 6 different Aldol reaction products.
So this happens with any base.
Yes, this happens with any base right here, yeah. And ketone or aldehyde.
Good. So in the last slide, it was CH3O. And so that'll just add an extra methyl group, right?
This over here, this ester.
Yes.
Oh,
No,
so
for number 1 on our first starting one, when you scroll down a little.
yeah.
this, wait, one more. On the arrow, the CH3O.
Oh, CH3, CH2O minus right here.
No, the other one. Where was it? Go up. Freeze. It's like number one. Yeah.
Oh yeah. So this is Claisen condensation. I use CH3O minus as the nucleophile because you usually use you see this piece of the ester right here, this OCH3.
Mhm.
You use the nucleophile that matches this ester's OR group, which this OR group is a CH3.
Oh,
Yeah, which is
okay.
different from this reaction over here.
Okay.
For this one, are the alpha 3 products more high yield or are they all the same yield?
They're all the same yield. Yeah. Oh, and this is for the Aldol condensation reactions only. I think your professor would want you to draw the full Aldol reaction with the dehydration step. So
Mm.
to do that, you know how the product is always going to be an enone.
Mhm.
Look at this product over here. We know that the alcohol is going to be gone, it's going to disappear. So I'm going to erase that and then just draw a double bond where the enone would be, which is over there.
And dehydration happens with heat and an
Base.
acid.
Oh, acid or base, but more commonly base.
Okay.
Yeah. And we do the same thing for all of these to complete the problem. Erase the alcohol and draw where the double bond would be to make the enone.
What happens to the hydrogen when you dehydrate it?
Oh, the OH group.
Alcohol. Yeah.
Yeah, so the OH group gets kicked off in basic conditions, but in acidic conditions, it first gets protonated into like a water-like molecule, and then it gets kicked off as water in acid conditions.
Okay.
Yeah, and I think I show the mechanism for basic conditions here. Let's see. Yeah, for aldol. Over here, dehydration of aldol. So this is in basic conditions. We have this aldol condensation reaction. We have an OH minus. This is the alpha carbon between the carbonyl and alcohol. We deprotonate that, make a double bond right there with the enone is, and just kick out the OH group, reforming our base catalyst.
Okay.
And this is our enone product for the aldol reaction. And we just did that same thing for all of these 6 products. Where we have an enone here, enone to check our answer.
Okay. That's not that bad.
Yeah, that's good.
I was scared. I was
Yeah.
like, this is too much to know, but it's all the same.
Yeah,
Most
it's all the
important.
same. It's just different nucleophiles and electrophiles.
Yes. But I think going over this is making it easier to recognize.
Yeah, that's good. And then when you do practice problems, you could use these tips when you do the practice problems to reinforce it more.
Yeah,
So
I really need to do the star and the dot.
yeah, that's new bond, the start and the dot between them. New bond.
I'm always missing the new bond. I think that's why.
Yeah. It's okay. That's a common mistake. A lot of students miss at least one bond, which is that bond.
Yeah. I'm like, why are they right next to each other? That doesn't make sense to me. But it makes more sense now.
That's good. Yeah. And also that new bond right here, the new bond between the start and dot carbon comes from this arrow right here. Because you see this arrow is when the start attacks the dot carbon. When the attacking happens, it forms the new bond. So you could think of it that way as well. So this new bond is basically this arrow right here. This attacking arrow. Okay. This is a crossed Claisen condensation, and there are 4 different products. So I'm going to label our different alpha carbons again. This is alpha 1. This is going to be alpha 2, let's look at alpha 1. Just gonna deprotonate it right away. We have a negative charge there. It could attack itself. This star the attacking carbon, dot the carbon being attacked. Star, and then usually to make this look more neat, you see how here the methyl group is going up in this direction.
Yes.
I'm going to make that methyl group go down this time. It's the same thing though. I'm just doing this to make this more neat. And that's the starred carbon. And I'm making the new bond right here. This is the new bond I just drew between the starred and dotted carbon. You see this new bond over here?
Yes.
Yeah. So that's the new bond. And then I draw what's attached to the dotted carbon, which is
O minus.
right, O minus, ethyl and ethoxide. And then we know, yeah, yeah, we reform our carbonyl, we kick out the bad leaving group, and then that would give us this, and then this bad leaving group will come and deprotonate that alpha hydrogen, but we know that the alpha hydrogen comes back by getting protonated in the second acids workup step. So I'm not gonna draw that because we know that this is the full answer at the end. But if he tells you to draw the mechanism during the test, draw that step. Like when the leaving group deprotonates the alpha hydrogen, and then that alpha hydrogen comes back from the second step over here. But to save space and time, I'm gonna leave this as the final answer over here.
My question is, so he says that there's like 4 different products. How do you know how many products will be formed?
Yeah, to tell how many products will be formed, I first identify all my different nucleophiles or all the different alpha carbons. So over here, we see there's only 2 unique alpha carbons, which is alpha 1 and alpha 2. In the other case, we had 3 different unique alpha carbons, alpha 1, 2, and 3. This is not a unique alpha carbon because there's another alpha carbon like that. It's symmetrical. After you identify all your unique alpha carbons, you attack every single possible electrophile there is. So it could attack itself, or it could attack the other molecule electrophile. So in this case, alpha 1 here could attack itself, which we did, or it could attack this other molecule. If there's like 3 ketones, then there would be way more products because it could attack itself, the second ketone, or the third ketone. So that would be like way more products.
That's way too much work.
Yeah, that's a lot. Hopefully he doesn't give you that on the exam because that would waste so much time for one single problem. Okay. So that's when this alpha 1 attacks itself, it could also attack the other molecule. So let me draw that. Dot that, start, attack the dot carbon, kick up the carbon up there. Do this. And to make this more neat, I'm going to shift the methyl group down here, make the new bond going up between the start and dotted carbon. That dotted carbon is attached to O minus, 1, 2, 3 group, purple group, 1, 2, 3, and ethoxy group. And we reform the carbonyl, kick out the bad leaving group, and this would essentially give us the final product after the bad leaving group deprotonates the alpha carbon and it gets reprotonated by the acid workup. But since this is just telling us to draw the products, we don't have to draw all those steps. We would only have to draw those steps if it tells us to draw the mechanism. Yeah, and that's the second product. And you basically do the same thing for alpha 2. It could attack itself. Or it could attack the other ester. And to make this more neat, this ethyl group here, I'm going to shift it downwards and make the new bond going upwards between the start and dotted carbon attached to O-, propyl group and ethoxide. We form a carbonyl, kick out the bad leaving group, give us our final product. Okay. 1, 2, 3. Okay, and then our last product is if this second alpha carbon attacks the other ester, which is going to be this. Shift the ethyl group going downwards, new bond between the start and dotted carbon. That dotted carbon is attached to O-, ethyl group and also ethoxide group. We reform the carbonyl, kick out the bad leaving group, and give us our last and final fourth product.
If we were to dehydrate this, will the double bond always be at the alpha carbon?
In this case, we don't do dehydration. Dehydration is usually only for Aldol reactions. This is Claisen.
Oh, okay.
Yeah. And you see how here for Claisen, to make sure that we have the right answer, we look for our beta keto ester. This ester here has a carbonyl or a ketone at its beta position. This is alpha, this is beta. So we have a beta keto ester here, beta keto ester, and beta keto ester. So everything checks out here. Does that make sense?
Yes, I feel a lot more confident now, knowing how to make better bonds.
Yeah, that's good. Okay. We're up to ketones. So Claisen condensation, this is the regular Claisen condensation that we did with the beta keto ester as the final product. And then from there, we do saponification, which we convert this ester into a carboxylic acid by doing hydrolysis. This is hydrolysis. Here we added base and water and acid, which converts this carboxylic acid derivative back into the carboxylic acid. And I think this is one of the previous chapters you learned before this chapter, which is just converting an ester back into the carboxylic acid, which is called hydrolysis. And then from here, we do decarboxylation, which is, I think, the newer reaction in this chapter, where if we have a beta carbonyl to a carboxylic acid and you add heat, this carboxylic acid here, right here, is going to emit off as CO2 gas right there. And I can show you the mechanism of this really quick. But I don't think you need to know it because your professor didn't go over it, but I'll just show it to you just in case.
Yeah, we did this last chapter.
Last chapter, yeah.
But for the saponification, how do we get rid of the OET, the ethoxide?
Yeah, so we need to go over the mechanism of this saponification. Okay, over here. It's kind of long.
I think I have an okay understanding. I'm assuming that ethoxide
Yeah.
becomes the leaving group, huh?
Yeah. So this OET is the leaving group. So what basically happens is this water here attacks the carbonyl, kicks up the carbonyl onto the oxygen, and then you know how the oxygen have a negative charge? That negative charge will come back down and kick out the OET. And then the water molecule will get deprotonated back into the OH. And that's basically the whole mechanism of that.
Okay,
Yeah,
I'll review that, but I think I'm okay.
yeah, that's good. So this is going to be our CO2 that leaves. Then we'll get this step happens because oxygen is really attracted to hydrogen because of the hydrogen bond. So oxygen attacks the hydrogen. This hydrogen and oxygen bond breaks and makes a double bond between this carbon and oxygen. And then this bond right here breaks and makes a double bond over here, which would give us OH like that. The methyl group goes up there. And then CO2 gas, which is this green thing I circled. And then we have
Enol.
an enol here, right? Which we do tautomerization right here,
Okay.
which is the answer right here.
Can you send us these slides that you wrote on?
Yeah, yeah. No shoot, but the ones I did with you guys live is kind of messy. Because
No,
I
it's
was
okay.
kind of
It's okay. I
rushing
can
it.
understand it.
Okay, that's good. Because the ones I prepared, I made sure that was neat. But then the ones I did live were kind of messy. Yeah. Okay. Yeah. Let me write taught here. Tautomerization. There you go. Okay. Yep. And then this results in a symmetrical ketone. You see how here the ketone we formed is symmetrical because both R groups are ethyl groups. With all these steps over here, Claisen condensation, saponification, and decarboxylation, they would always yield a symmetrical ketone. That's just a concept or like a thing to check your answer.
Wait,
So
can you go back?
yeah.
Really fast? One more slide up.
Yeah.
And so this methyl group is
Oh, this one right here?
yes.
Yeah, so
That's the
this methyl
methyl
group is this methyl group right here.
Okay.
And this green circle is this CO2 right here.
Got it.
And this hydrogen here is this hydrogen now.
And then tautomerize it.
Yeah.
Okay, that makes sense.
Enamines. Yeah. So when you have a secondary amine and a carbonyl, you're going to form an enamine here. He didn't go over the mechanism, but I don't know if you need to know that. We could go over it really quickly.
Hold on, let me check my notes to see if he did it.
Okay.
But enamines will always occur with this guy.
Yeah, with secondary amine. If you have a primary amine, then you'll form an imine, which is different than enamine.
Where the heck is it? Okay. He went over alkylation and acylation, but
Oh, of an enamine?
yeah, but not really the whole mechanism of
Yeah, like to form the enamine first in the first place, right? So yeah, I don't think you need to know that then.
I just need to know that it'll get rid of the oxygen.
Yeah. A trick to think about this is like it gets rid of this oxygen right here, and it makes a new bond where the oxygen was to this nitrogen right here. And this nitrogen just loses a bond and then reform a double bond right here. That's the general trick.
And the acid catalyst helps form the water.
The acid catalyst helps activate this electrophile because the very first step of this mechanism is that this carbonyl carbon gets protonated. And then this carbonyl carbon here is now very electrophilic and ready for this amine, secondary amine, to attack and go on with the mechanism.
Okay.
But he didn't go over the mechanism, so I don't want to like overwhelm you with like too much information that's not going to be tested.
Yeah, I just need to know how to make the nucleophile.
Yeah, which is this one over here. And so the reason why I drew this resonance form is because I'm explaining why this carbon here, the beta carbon, is the nucleophile, because this resonance form is the less stable one, which makes it the more reactive one. And since it's more reactive, this is the nucleophile. Since this table is more stable, it's less reactive, which would not be the nucleophile.
Got it.
And then this is for alkylation here. We could do SN2 reaction. We know that this is an enamine right here. This beta carbon is the nucleophile. The mechanism is that we reform the double bond between the carbon and nitrogen, and then use this double bond to attack this electrophilic carbon and kick out the bromine. This is the SN2 reaction here, where I starred the attacking carbon, which is this beta carbon. I dotted the carbon being attacked, which is that carbon holding the halogen. And then I made a new bond right here. This is the new bond between the starred and dotted carbon. And then I drew what was attached to the dotted carbon, which is this R group right here. The BR is not attached anymore because I got kicked off over here. And this nitrogen here now has a positive charge because it has 4 bonds now. 1, 2, 3, 4. Does this make sense so far?
Yes, but it's not gonna stay like that. Okay.
Yeah, it's not gonna stay like that. This gonna be an intermediate.
Okay.
And it's the reason why it's racemic is because you know how here this was the sp2 carbon. This sp2 carbon could either attack this on the top or bottom side, making this either be a wedge or dash, but I don't think that would be tested as much.
No, we barely went over that.
Yeah.
The chemistry for this.
Mm-hmm.
But could it also attack the alkene?
Attack this alkene right here.
Mm-hmm.
So this alkene here does not have any partial positive charges, so this won't be the electrophile, so it can't attack the alkene. No.
Oh, okay.
Yeah, that's later on. When you learn about enones, which you will attack the alkene. But in this case, this is not an enone, so you won't attack the alkene here. And then from there, we use acid and water to get rid of this whole amine mess and just replace that with a carbonyl. And then that whole mess gets get kicked off as this protonated version over here, because it's in acidic conditions. And here's the mechanism for that. But since you didn't go over it, I don't think you need to know it. So you want to just skip over this part, or walk through it?
We slightly went over it.
They went over it. Okay.
Yeah.
So you see how here this nitrogen here is positively charged. Since this nitrogen is positively charged, this carbon here is going to be a very good electrophile, where this weak nucleophile is able to attack that electrophile and then kick up the double bond to the nitrogen. So here's the carbon that was attacked by the water, and then this double bond got kicked up onto the nitrogen, giving it a lone pair and neutralizing it. And here's the proton transfer step. We are going to protonate the group that we want to leave and deprotonate the group that we want to stay. So we want the water group to stay. So we're going to keep deprotonating him until it's neutral. And then we want this amine group to leave. So we're going to keep protonating that amine group until it becomes a good leaving group with a positive charge. So first, I just deprotonated this water group to make it neutral into the alcohol because we want it to stay. And then I protonated this nitrogen group to give it a positive charge. And that's a good leaving group now. And to give it a reason to leave, I have this lone pair of electrons onto this oxygen, kick back down, reform the carbonyl bond, and then kick out the good leaving group that we just formed, which is this group right here. And then we have this oxygen double bond with a hydrogen and a positive charge. So I redrew this whole thing. I neutralized it by deprotonating it. And then at the very last step, since we're in acidic conditions still, I just protonated the amine to get our side product.
What if, so usually when we do HCl over water, we do H3O plus. Would it instantly go to the third step.
Like third step,
That one, yeah.
like H3O
When
plus.
the nitrogen gets protonated.
Yeah, yeah.
Okay.
And then after it gets protonated, it becomes a good leaving group, where we kick it out by reforming the carbonyl bond here.
Mhm.
And then it gets kicked out over here. And then it could also either grab the H3O plus or HCl. I just use HCl because they gave us HCl here, which is a stronger acid than water is.
Stronger acid than water. Yes.
You could have also used HCl over here, but since we formed H3O plus from this water, I just used H3O plus. So you could use H3O plus or HCl. You still get the same answer
Okay.
since they're both acids.
Okay.
Mhm.
This is pretty new to me. I was trying to study this part, but
This mechanism.
yeah, I was
Yeah.
getting confused.
Yeah, he didn't go over in detail. He just like skipped straight to the product.
Oh wait, I'm looking at the acylation, not the alkylation, but yeah, he mostly skipped through it.
Yeah. Yeah, this is the acylation over here.
What's the difference between the two?
Yeah, so acylation is when you're adding on a acyl group, which is a carbonyl. So you see how here, so alkylation is just adding an alkyl group, which is an R group. We see here this alkylation. You see how here this is just a random R group with no carbonyls onto it.
Mhm.
Since it's just an R group, that's alkylation. But for acylation, we add an acyl group, which does have a acyl group, which is a carbonyl group,
Got it.
basically. Yeah. And here's the mechanism for that. We use the acyl halide, which is this acyl halide over here. We form the double bond between this carbon and nitrogen. Use this alpha carbon to attack this carbonyl carbon. Kick up the carbonyl bond onto the oxygen right there. We reform the carbonyl, kick out the good leaving group chlorine. And also you notice how here I started attacking carbon and dotted the carbon being attacked.
Yes.
I made that new bond between them, and then I drew whatever was attached to the dotted carbon, which is an O minus, a methyl, and a chlorine. And then I reform the carbonyl, kick out the good leaving group chlorine, giving us our final intermediate here.
Got it.
And then it's the exact same step when we use water and acid. We just get rid of this imine into a carbonyl.
Comparatively imine. Okay.
Yeah. And that mechanism is over here. But just with different structures.
Yeah, I'm not gonna worry too much about the water and HCl part. I'm just gonna know it makes the carbonyl.
Yeah, this part over here. This important mechanism right here.
Mhm.
Yeah.
Oh yeah, I think I do need to know that part. I was mixing up that with the last that
Oh, this one?
yeah. I was
Yeah,
like,
this is just turning this imine into a carbonyl. Yeah. Which is longer than this one.
yeah, this one's
Yeah.
nicer.
Yeah, yeah.
Okay, this one's on the exam, so I definitely need to.
Oh, on Thursday's exam, not on Tuesday's quiz.
I think it'll be on the quiz and the exam, but he didn't really go into the mechanism. He mostly just was like, know the steps really well. Yeah.
Let's see. Yeah. Okay, let's go over it. So, acetoacetic ester synthesis is going to produce a mono or disubstituted acetone. So an acetone, I'm going to highlight the acetone here. It's basically this ketone with two methyl groups. You see my highlighted acetone.
Yes.
We could either have a mono-substituted acetone with only one R group or a di-substituted acetone with two R groups right there.
So when we do this reaction, it'll always be acetone and then the group that you add.
Yeah.
Okay.
And this will come from acetoacetic ester. So the aceto means this 2 carbon like group right there, and it could be any ester. So let me write this down. Aceto is the yellow part, and then acetic ester. Yeah, this is your starting reactant here. You could either get the monosubstituted or disubstituted acetone.
Are they both equal yield or one is more?
It depends on what we're given. This disubstituted acetone here requires more steps. This monosubstituted here requires less steps. And I'll go over that right here. Yep, the R group monosubstituted. Yeah, this is what we just went over. You see they had it the acetone, and then this is the R group right here. This is monosubstituted. So here's the mechanisms. Step 1, this is the acetoacetate. We do a Claisen condensation. Actually, we don't do a Claisen condensation. You see how here this alpha hydrogen here between these 2 carbonyls is the most acidic hydrogen. We use ethoxide as the base to deprotonate it and make our nucleophile here. And this is our nucleophilic alpha carbon here. That's the first step, forming the enolate anion. The second step is the SN2 reaction where we use that nucleophile to attack the any electrophile, which is going to be an RX, usually an RX, an alkyl halide for SN2 reaction, and that adds onto our R group here. So I started the attacking carbon. I dotted the carbon being attacked. I did the SN2 reaction, kick out the good leaving group. I made a new bond between the starred and dotted carbon, and I drew what is attached to the dotted carbon, which is this R group over here.
Okay.
Yeah, and that's the monosubstituted version. That's that. But if you want to do di-substituted, then you just do it. Let's see one more time. Di-substituted is later, but to keep going on, you see how here we have the ester here.
Yes.
We're going to hydrolyze that because since this is a carboxylic acid derivative, we're going to hydrolyze that back into the carboxylic acid using a base and acid and water. And then since that's a carboxylic acid with a beta carbonyl, once we add heat, this carboxylic acid just emits as a CO2 gas. It disappears. And actually, you do the mechanism in the previous slide. Does that make sense so far?
Yes, I'm definitely gonna have to go over saponification.
Oh,
But
saponification, like this step over here?
mhm,
Yeah. I think you went over that on the previous chapter.
we did, but okay, so I just have to know that the ethoxide just becomes an alcohol, right?
Yeah, this OR group here, ethoxide or any OR group, propoxide or anything, just becomes OH.
Okay.
Yeah.
That's
It's so hot
it is
today.
hecka hot. It's like
Yeah.
103 here.
Yeah, I'm like sweating. Yeah. So now let's move on to the di-substituted acetone. We start with the monosubstituted intermediate before we did the saponification step, which is this over here. We start with that, and then we do the exact same thing. We form the enolate anion by deprotonating the alpha hydrogen, giving us our enolate anion nucleophile, and then we do the SN2 reaction by bringing in an RX. This is the starred carbon, this is the dotted carbon. SN2 reaction adds the other R group there. And then we do saponification and then decarboxylation at the end. So it's basically the exact same thing, just happens a second time to add on to the second group.
Can you scroll up a little?
Yeah.
Okay, so we make a new nucleophile, and then this guy's gonna get that guy. Okay, and that for that second step, it'll be any chain, right?
Yeah, it could be any chain. It could be benzene ring. It could be a propyl group. It could be a super long chain. That is just gonna be this group over here. So if it's a super long chain, then this carbon would be longer right here. This chain right here.
Mhm.
And that's
And-
alkylation because we just alkylated it. We just added a R group, not a acyl group.
Okay, so it'll be acylation when if we add like a carbonyl.
Yeah, an acyl halide, which is this over here,
Okay.
or an anhydride, but more commonly you say acyl halide.
Okay.
Mhm. Oh, okay. Malonic ester synthesis. So it's the exact same thing as what we just did, but you see how here we started with a one ester that has a carbonyl in this beta position. For
Okay.
malonic ester synthesis, we start with two esters, which is this right here. This is the reactant right here. Before, you know how we didn't have this OR group?
Yeah.
Now we have that OR group giving us two esters here.
And it's not always gonna be like symmetrical.
Yeah, it's not always going to be symmetrical. That's right.
Okay.
And then we could have a monosubstituted acetic acid where we have a carboxylic acid here. So acetic acid is basically a 2-carbon carboxylic acid. So I'm going to highlight the acetic acid. This is the acetic acid here, acetic acid here. It could be monosubstituted with only one R group attached, or it could be disubstituted with 2 R groups attached.
How about tri-substituted?
Trisubstituted, let's see. That won't happen because there won't be a alpha hydrogen to deprotonate to make a nucleophile again, because you see how here for the disubstituted thing we had another alpha hydrogen to make the nucleophile, the enolate anion, to attack another RX group to alkylate it. In this case, if we wanted to do a tri-substituted thing, there would be no alpha hydrogen here. Since there's no alpha hydrogen, we can't have a tri-substituted product.
What about there's alpha hydrogens on the left side?
That won't be like that's something else. That would be that's not the most in this case that would be the most acidic hydrogen because there's no other alpha hydrogen between these two carbonyls, but that won't be tri-substituted because in that case that's a different carbon. That would be monosubstituted for that one carbon.
So you can keep adding carbons on that side?
Yeah, if you add a strong enough base like LDA or something like that, yeah. But it won't be tri-substituted, it will be monosubstituted. Okay. Yeah, this is what I talked about. This is the acetic acid, and this is the monosubstituted thing because we have this one R group here. So the steps of this mechanism would be to deprotonate the most acidic hydrogen, which is the alpha hydrogen between these two carbonyls here. So right after we deprotonate that, we form our nucleophilic enolate anion in the first step. And then the second step, we just do SN2 reaction and alkylate that group right here. I start the attacking carbon, dot the carbon being attacked, and then make a new bond between them. And then after that, we do the saponification. Since we have two ester groups this time, not one, we're going to convert these two OR groups into OH groups here. And then for the decarboxylation group, we just get rid of one of the carboxylic acids as CO2. I chose the left one to get emitted as CO2. And this whole R group here just gets shifted to the left right here. Does that make sense so far for the mechanism?
This is number 3.
This is step number 4 for decarboxylation. The first step is to make the enolate anion nucleophile.
Mm-hmm.
The second step is to do SN2 reaction.
Okay.
And then the third step is saponification. And then the fourth step is decarboxylation.
Is MEO just a methyl?
Yeah, Me is a methyl. O is the oxygen.
Okay.
Yeah.
Yeah. Makes sense. It's kind of similar to the other one. It's like-
Yeah. It's like the exact same thing, just another ester group, like 2 ester groups instead of 1.
Mhm.
The other one just had a ketone. Okay, so let's do the micro reaction.
Okay. I know I need to know this one.
Yeah. Okay. So for the micro reaction, the enolate anion attacks the 4th position of this enone. So we have an enone here. The way we number this is 1 on oxygen, 2 there, 3, 4 there, and 4 there. If a nucleophile attacks this 4th position, that's a 1,4 addition. If a nucleophile attacks this 2nd position, that's a 1,2 addition. And weak nucleophiles can only attack the 4th position, and strong nucleophiles can attack the 2nd position. And the reason why is because let's look at this enone over here and draw its resonance form. So I move the double bond down here, kick up the carbonyl bond onto the oxygen. You see how here this 4th position has a bigger positive charge than this 2nd carbon? Since this 4th carbon has a bigger positive charge, it's a stronger electrophile. So weak nucleophiles can attack that strong electrophiles. It cannot attack the weaker electrophile. Only strong nucleophiles can attack this weak electrophile. And strong nucleophiles are organometallics like RMGBr, RLI, reducing agents like Li, ALH4, or NaH. And everything else like enolates, CN minus are weak nucleophiles. So let's go over the mechanism. We have 2 esters here. This is the alpha carbon between these 2 esters. This ethoxide here is going to deprotonate that alpha hydrogen, form our enolate nucleophile here. And then we bring in our enone here. This is a weak nucleophile, so it can only attack this 4th carbon over here. So I star my attacking carbon, I dot my carbon being attacked, and I attack that carbon, move the double bond over here, and then kick up the carbonyl onto that oxygen right there. And then to connect this, I make the new bond between the starred and dotted carbon, and I attach what is attached to this blue dotted carbon, which is this 1 bond that does not have the double bond anymore. And then next to that is a double bond with the O- and the methyl group. And then I protonate this O-, which gives me an enol here, and then I do keto-enol tautomerization into the carbonyl.
That's our final product.
Yeah, that's the final product for micro addition. Yeah.
Oh, that's not bad. And this
Yeah.
is usually 1,4 addition, right?
Yeah, this is just for 1,4 addition, right? Right.
Okay. Yeah, when we were learning this, I was so scared and stressed.
Yeah, like it's so like so much things going on, right? Like at UC Davis, this is the chapter where a lot of students like start to lose hope or like get overwhelmed because of these like
Steps.
these steps, and because like these steps are like usually longer than the other reactions they've been learning.
And it's like so many bigger molecules.
Molecules,
too.
yeah, like combining them together too.
So for microreaction, it's usually with,
Oh, 1,4 addition. Think of micro addition as 1,4 addition.
okay.
Mhm.
And it's always with an alpha beta carbonyl.
It doesn't have to be that way. It could be enolate. Yeah. It's always with the alpha beta carbonyl. Yeah, you're right. You're right.
Okay.
Yeah.
Okay. I definitely have to go over this one because I stopped over here. I was too
Yeah, too overwhelmed.
hesitant.
Yeah.
But it doesn't seem as bad when you go over it.
Yeah, just do a lot of practice and then it will start to click more.
Yeah. Everything seems mostly the same.
Yeah. A lot of general patterns going on here.
Mm-hmm.
And then this is just basically showing like what I did before, why this is the more strong electrophile and the mechanism, we went over that already. Oh shoot, I think the Zoom, there's a delay on like when I scroll on my iPad.
Mm,
Yeah, because like when I scroll, like it doesn't like sync in directly. Yeah.
oh, really?
Yeah.
It's okay. We didn't notice.
Oh, okay. So yeah, we went over the mechanism already. Um
What is
Michael, yeah. So this right here is the Aldol reaction. We did that before. Aldol is when we have an alpha enolate anion here attacking a carbonyl, which is this is the carbonyl here. For Michael reaction, we add to the fourth position of the enone, which is a 1,4 addition. This is just a resonance form of that.
Can you
This
can you go over the counting? Because I know it's like count,
like to combine the product here.
like I know when it's like 1,4, it's not necessarily like the first carbon.
Yeah. Let's see here. So this is weird because usually when we do nomenclature, we only do carbons as one, but for this case, we do oxygen of this enone as one, and then the carbonyl carbon as two, and then this as three, and then this as four.
Okay.
And then if we do the, let's say, resonance form of this is gonna be the exact same thing.
And this could like react with, can it react with itself like how we did with like Glycine and stuff?
For enones.
Was it Glycine? Or when it reacts with
Oh
itself?
yeah, with Glycine and Aldol. No, this won't attack with itself because enones it can't make a like a nucleophile by itself. No.
Okay.
Yeah. So does this make sense so far?
Yes. So our first step is making our nucleophile with ethoxide.
Yeah, ethoxide or any base.
Any base at the
Mhm.
alpha carbon.
Yeah.
And then our next step will be protonating the oxygen.
So after we do the deprotonation to make the alpha anion, the second step is to do a 1,4 addition to attack the fourth position first.
Okay.
And then we protonate the oxygen. And then we do keto-enol tautomerization, and then that's it.
Oh, that's so easy.
Yeah. It's only like 3 steps, but it's big molecules, so it looks like a lot.
Yeah. It was
Yeah.
giving me a headache trying to understand, but it
Yeah.
looks a lot better.
I think it's harder combining the molecules than the actual steps itself.
Yeah, I think the trouble where I could find myself is knowing which part or remembering that it doesn't attack the carbonyl.
Yeah. It doesn't attack the carbonyl. Only these things do. The strong nucleophiles, organometallics, ALIH4, and NAH.
Are we gonna go over that part or no?
Yeah, we are later on.
Okay, I'll let you just continue.
And these are just a list of nucleophiles, the weak nucleophiles that does 1,4 addition. Yeah, let's see
Yeah.
types.
I'll go over those.
Enamines can also participate in microreactions, because you see how here this is the enamine right here, and this beta carbon is the nucleophile. This beta carbon nucleophile is weak. It attacks the fourth position. So in this case, this is weird because you see how here this is not an enone, but an alkene next to a nitrile.
Mhm.
It's like an enone because you see how here I drew the resonance like this, and we have a positive charge on this carbon
Yes.
and a negative charge there. This beta carbon is going to attack that positive charge right there. And then I start the attacking carbon, dot the carbon being attacked, make a new bond between them, and then draw what's attached to the dotted carbon. And then from here, I reform the triple bond between carbon and nitrogen. And then you see this carbon here, I have to grab a hydrogen and kick out like from an acid, from any acid. And this gives us our nitrile, regular nitrile back with the imine here.
Hold on, I do have one question. What does it mean? What's saturated versus unsaturated?
Yeah, so saturated is no double bonds or triple bonds. Unsaturated is at least one double bond or triple bond.
Okay.
Mhm.
But why does the beta carbon attack? Why doesn't the alpha go?
Oh, like this alpha carbon here?
Yeah.
Yeah, that's because let me draw you the resonance structure of this enamine here. So we know that this nitrogen has a lone pair of electrons. When we do the resonance form by reforming this double bond between that carbon and nitrogen, this double bond here can only go onto that carbon.
Okay.
And that gives that carbon a negative charge.
Okay.
And the alpha carbon would never have that negative charge,
That makes sense.
which is why the beta carbon is the nucleophile, not the alpha.
Okay. Perfect.
And then you could also use this to do this mechanism. Like you could just draw this straight up right here instead of this, and then use this to attack because this will end up as a product as well. This positive charged nitrogen right here. Yeah. And then everything else here, you know how we convert this imine into a carbonyl with acid and HCl. I mean acid and water, yeah. Like H2O and HCl. That this is the whole mechanism for that, but he didn't go over that much, so I don't think you need to worry about that. You just need to put H2O, HCl, and then convert this whole imine into the carbonyl.
Okay, I'll remember.
Yeah.
Here we go.
Oh, yeah, this is the 1-2 edition now, where we use strong nucleophiles like RLI or RMGBr. In this case, pH is phenol, Li is lithium. So pH, you can think of that as an R group. This RLI here is a strong nucleophile, where whatever is attached to the Li or MGBr is the strong nucleophile. In this case, we have an enone. Let's label this 1, 2, 3, 4. Since this is a strong nucleophile, it could attack the weak electrophile here, 1-2 addition. So I started the attacking carbon, dotted the carbon being attacked. Here's the new bond between the starred and dotted carbon. The Li just like dissolves away in the solution. The blue carbon is attached to this R group, this methyl group, this O minus, and then the Li dissolves as a plus, so that's why it's like ionically bond together. And then from here we just protonate the O minus with the acid workup step.
Okay, this one's not as bad.
Yeah, it's a little bit easier.
Yeah, it looks good.
Yeah,
And
because it's like normal one. It's like normal carbonyl attack.
yeah, and same with like what, Grignard?
Yeah, like MGBR. This could be MGBR as well.
And any group attached.
Yeah, the RMGBR.
Okay, perfect. I fell asleep during this. And
Oh, during this part right here?
Yeah.
Yeah.
Wait, did you Was there a slide on using LDA?
Yeah, that's later on.
Okay. Just wanted to make sure.
Yeah.
Yeah, he was like, I'm gonna ask whoever falls asleep a question, but I wasn't writing any of it.
Uh-huh.
Well, obviously, I'm gonna fall asleep. I was heck mad.
Yeah. Wait, did he call you out? Like did he ask you questions when you were falling asleep or something?
No, he didn't ask me, but I was so mad
Mhm.
because it was like, oh, it was more towards the end, and he just kept talking about kinetic and thermodynamic. And I was like, if it's not really gonna be on the test, why am I gonna stress about it?
Oh, this is not gonna be in a test?
I mean it is, but he was like, you don't really need to know this, just have an understanding.
I see. Dang, yeah. I think professors just do that to like fill up time and like make sure like they cover like the right amount of content for the textbook.
Yeah.
Yeah. Wait, what is that gonna be on your quiz this Tuesday, chapter 19? That's it?
19 and 20, and then we should be doing 21 during the week. But 20
Oh.
mostly benzenes and aromaticity. And
Mhm.
I think from Okuda I learned a lot from that. But
Yeah.
I'll
But
send you chapter 20 tonight.
yeah, the PowerPoint.
Mhm.
Yeah, that's good.
We mostly
Wait,
just
well, does the midterm go over the same material as the quiz, but it's just like longer, or does the midterm cover more stuff?
the midterm, it's fairly similar because
Mm.
compared to the quiz, we basically have to know the same mechanisms.
Uh-huh.
And he'll ask the same, plus like whatever we didn't go over on the quiz. But it'll only be on 1920 since we haven't finished or even started 21.
Yeah. See.
It's gonna be
So for thermodynamic and kinetic control, um, we have an enone here, and this is a nucleophile. This nucleophile could be strong or weak. If it's strong, it does a 1-2 reaction. If it's weak, it does a 1-4 reaction. And 1-2 reactions, you could think of that as a faster reaction, because it directly attacks the carbonyl carbon. So in this top case here, this fast reaction, you see how the nucleophile is attached to the second position, 1-2 addition?
yes.
And then the O minus gets protonated to OH. This is a less stable product. 1-2 addition, and let's see here, more stable products. I'll show you why this is the less stable product than this one after I go over the bottom reaction.
Mhm.
The bottom reaction is a slow reaction. It's a 1-4 addition because you see how here the nucleophile is attached to the fourth carbon now.
Yes.
And then this O minus gets protonated to OH. We have an enol here. We tautomerize that enol into the carbonyl. This is more stable because let's compare the double bond. You see how here this double bond is the double bond between two carbons.
Yes.
The double bond on the bottom position is a double bond between the carbon and the oxygen. So that's a carbonyl bond. This double bond is going to be stronger because this oxygen is way more electronegative than this carbon is. So there's a polarity between them.
Mhm.
And if there's a polarity between them, they have dipole moments, and then they can bond with each other more. They have more intermolecular forces, making this stronger than this double bond between carbons only with no dipole moment.
And this happens with the same nucleophile.
Yeah, but no, not the same nucleophile. The bottom one is a weak nucleophile because you know how it did a 1-4 addition, and 1-4 addition is only for weak nucleophiles. The top one is a strong nucleophile because it did a 1-2 addition. So think of the top ones as um R, MGBR, R, LI, LI, ALH4, or
Yeah.
NaH. And then everything else, like basically like majority of the nucleophiles are the bottom one. Like the
Li
enolate.
LiALH4 will just remove the double bonds, right?
Yeah, it would just remove the double bonds and add hydrogens.
Okay.
And that's the same thing as NaH.
Okay.
And R, MGBR, RLI will add R groups onto the second position.
Mhm.
And it only does that to the double bond between the carbon and oxygen, not the other the double bond here.
Okay.
Because it's a 1-2 addition.
Okay. That makes a lot of sense. Why is it irreversible for strongly basic?
Yeah, for strongly basic carbon nucleophiles like RLI or RMGBR, you could think of that as like, since it's very basic, it wants to grab a hydrogen and it wants to keep the hydrogen. It doesn't want to go back. Like it doesn't want to give it up once it has the hydrogen.
Mhm.
So it's not reversible. It's
Okay.
irreversible. So when you do the mechanism, you just put like a arrow, single-headed arrow.
Perfect. Robinson.
Oh, Robinson annihilation, that's a long mechanism.
Oh yeah, he didn't go over it.
Oh, yeah, because it's really long. Yeah,
Yeah,
it's really long.
just like know what happens, but is it
Yeah.
going to be the same? Like, so it's just like a micro reaction?
Yeah, so basically it's a micro reaction where you see how here this is the alpha carbon between the carbonyl and the ester.
Uh-huh.
This alpha carbon will get deprotonated into the alpha enolate anion nucleophile. And then which carbon would it attack? Would it attack this carbon or this carbon?
It'll attack at 1,4. So
Yeah.
the alkene.
Yeah, this one right here. Yeah. Once it does that, we get this whole thing right here. That's the micro addition. The first step is micro addition. And then the second step is Aldol reaction, where you see how here we could do enolate anion again with this alpha carbon right here.
Okay.
This is an intramolecular Aldol reaction. So this enolate anion here will attack this electrophile. You see this carbonyl electrophile?
Mhm.
And that gives us our 1, 2, 3, 4, 5, 6 membered ring. 1, 2, 3, 4, 5, 6. But you know how here when we attack this 6 carbon, we kick up the double bond onto the oxygen with the O minus.
Yeah.
That O minus gets a hydrogen from like an acid or something.
Mhm.
And then from here we do the aldol dehydration. We get rid of the OH and get our enone.
So does it attack that alpha hydrogen, this alpha carbon, because it's just closer?
Yeah, this alpha hydrogen is the most acidic hydrogen because it's right between the two most electronegative atoms.
Okay.
And then once it does that, it is going to form a double bond right here and then kick out the alcohol group right there, forming our enone here.
And it wouldn't attack the other alpha hydrogen or alpha carbon, right?
This one right here?
Yeah. Why
No,
not?
it wouldn't, because this is less acidic than this alpha hydrogen here. We go for the most acidic alpha hydrogen.
Okay.
And here's the whole mechanism for you to review when I send it.
Got it.
Yeah. Okay.
Yeah, this one is more of like a discussion and know what happens kind of reaction.
Yeah, this is retrosynthesis right here. Retrosynthesis of microreaction. So you see how here this arrow looks kind of weird, like with the bar and the arrow.
Mhm.
This arrow in organic chemistry means going backwards in synthesis.
Mhm.
So over here, we could say that this was the
Acetone.
yeah, the acetone with the ester group with the alpha enolate anion, because I started here and I dotted this here. Imagine this thing, right? With enone right there. We could say that that came from that enone, and we could make a split between here by going backwards.
Mhm.
Split between the new bond that formed going backwards. So since we made that split, going backwards, we added a carboxylic acid here because let's say going forward, what reagent would get rid of that carboxylic acid with the beta ketone?
Water?
Think of decarboxylation. What is the reagent for decarboxylation?
Joseph, do you know? What is it? Is it just another acid?
It would be just heat.
Oh,
Heat.
heat.
Yeah, because when you have a carboxylic acid next to a beta carbonyl and you have heat, then this carboxylic acid just emits away as CO2 gas.
Okay, I need to remember that.
Uh-huh. And then from here, going backwards again, we cut the new bond in half, which splits up this beta carbonyl ester or beta keto ester. And then we could just add a double bond right there, giving our enone. So we know that this is our alpha enolate anion nucleophile. This is our electrophile, 1,4 addition, and then we go for it there. So this is just for like a synthesis problem, like the way to think about synthesis. Like
Mhm.
if you want to think about what your reactants are, this is a way to think about it, which is retrosynthesis. So going backwards, we could say that the carboxylic acid was there, but it disappears because of the decarboxylation. And then from here, we could say that this is the new bond that we formed between the beta keto ester and the enone. We cut that in half and then give back the double bond for the enone right there.
Wait, that's an ester turned into a carboxylic acid. So is
Yeah.
that the malonic ester or something?
Yeah, this is malonic ester thing as well.
So malonic esters is a carbonyl group, and then
Oh wait, malonic ester is something else. Malonic ester is when we start with two esters. This is only one ester. This is one ketone. So this is aceto something. This is the acetoacidic uh acetoacidic ester synthesis.
okay.
Acetoacidic, yeah.
Saponification.
Yeah, saponification hydrolyzes an ester into a carboxylic acid.
I could send the last chapter too if you want to go over saponification soon, Joseph.
Okay.
This one's too many steps. No wonder why he doesn't want to go over the mechanism.
Oh, he he didn't go over the mechanism of the saponification.
I think he did. He went over that one, but not for the Robinson.
Oh yeah, Robinson is crazy.
Yeah, I don't like it.
Yeah, here's the Robinson mechanism.
I don't
I
even
know.
remember it. I don't think Okuda taught it.
Yeah, I don't remember learning this.
Yeah. Robinson is basically a mixture of reactions: Michael, intermolecular aldol reaction, and dehydration.
So first we do Michael to make a nucleophile ready for intramolecular bonding.
Mm-hmm.
And then we do the aldol reaction to do the intramolecular.
Yeah, intramolecular after you do Michael reaction, intermolecular aldol reaction. And then after that, you have this Aldol condensation product. You do dehydration to get the enone.
And what's dehydration with again? Heat.
Yeah, with heat and base
Heat and base. Okay.
for base catalyzed.
Yeah, I know he taught us acid catalyzed, but I'm just gonna do base since it's easier.
Yeah. Yeah. He said base is more common on his slides.
Yeah.
Yeah.
So I don't know why he bothers teaching acid.
Acid. Yeah, that's a longer way too. The acid is longer than base.
Yeah, I noticed in my practice problems I'm always doing base.
Mm-hmm. Okay. Gilman.
Is this
No.
the copper? Yeah, copper one.
Yeah. You know how the strong nucleophiles are organometallics like Grignard RMGBR or organolithium RLI?
Yes.
If you want to add an R group onto the enone, but you want to do 1,4 addition instead of 1,2 addition, you use a weaker organometallic, which is a Gilman. And a Gilman is R2CuLi. And the R just attaches one time. So in this case, you see how here we have CH3 2CuLi?
Mhm.
This CH3 attaches to the fourth position only once right here, which is this CH3 right here.
So this is the only organometallic compound that'll give us 1,4.
Yeah, Gilman.
Okay.
Is it because it's more substituted or?
Yeah, it's more substituted, making it weaker, and something about copper, which is a metal, and that's goes into inorganic chemistry, which I did not learn.
Are you gonna go over the mechanism?
Oh, for Gilman?
Yeah, just really fast. I kind of remember it, but I kind of don't.
Yeah, let's go over the mechanism of this.
Perfect.
Hmm. Okay. And then three, two, C, O, I.
Very cold and ether.
H2O,
Have you
HCl.
done these mechanisms in the lab?
In the lab, I think I have in 118. Yeah, in my last quarter of UC of not UC of OChem. Yeah.
I can't remember if we did this. You know what happened in one of my labs?
What happened?
I spilled some of the thing I was supposed to make.
Uh,
So I restarted it. And then
uh-huh.
he was dehydrating it. Or yeah, he was adding, what was it? Something. And he freaking spilled all of the reagent I just remade.
So did you have to like stay overtime or what happened?
No, he was like, your percent yield's because of me, so I'm gonna excuse it.
Oh, that's good. Your TA or your professor?
My professor, we don't have a TA.
Oh, I see. I see.
But I was
It's a
so
small
mad.
class anyway.
Yeah.
It's small. And we're still averaging hecka bad.
I doubt you need to know this mechanism, but it's useful to understand it to remember the reaction more.
Mhm. Let me see if I have the notes on it too. I've been making cheat sheets of everything, every chapter I've gone through.
Mhm. That's good. That's good.
Yeah, I have this one. Ah. Also have my quizzes that I scored really badly on.
Here, here, and then
Gilman, here we go.
um, I'll just do acid workup.
So that's from the first step.
Yeah. So the first step here, we have the Gilman here, the R2, in this case, our R is methyl, CH3, CuLi. What none of the R group CH3 will attack the fourth position because this is a weak nucleophile. 1, 2, 3, 4. After it attacks the fourth position, moves a double bond here, kicks up the carbonyl up there, and then I start the attacking carbon, which is the methyl group. I dot the carbon being attacked, which is this fourth position, and I make the new bond. This is the new bond right here. You know, I just made the H3s invisible, but it's implied right there.
Yeah.
And the O minus is right there. The lithium, is positive, so they ionically bond. This copper is now neutral. From here, I just neutralize the O minus with the acid. We have our enol, and then I did tautomerization back into the carbonyl.
Got it. I don't like that mechanism.
Yeah, it's ugly.
It's hecka ugly.
Yeah, it's inorganic.
This is inorganic? Oh, it is.
Yeah, copper, magnesium, tin, zinc, any metal is inorganic.
So that can't go into the organic compound thingy.
No. This is organic right here. This stuff, and this is inorganic. The R2COI. LDA is strong, bulky base. Enolate anion formation can be driven to completion. Irreversible. Most commonly used for this is LDA, and then this is formation, but that's just lab stuff.
Isn't LDA for like E2?
Yeah. It could be used for E2. It could also be used for um Claisen condensation, Aldol reaction, or any enolate reactions. And for elimination reactions, LDA will go for the Hoffman product instead of the Zaitsev. But in this case, we're going over enolate reactions, which the LDA can be a base to form alpha enolate anion nucleophile. But in this case, if we use LDA, it goes irreversible, single-headed arrow. You know how in the previous cases with the enolate reactions, we did reversible arrows? That's because those were weaker bases. It could go back and forth. It could like readily give up its hydrogen again and go back and forth. But in this case, we have a strong base, so it goes into completion. And it's irreversible, so it can't go back. So we're stuck into this enolate anion nucleophile. And this is just a concept thing.
Yeah, I think we barely went in. Oh, we did go into the mechanism a little bit.
Yeah. After you have to eat so this LDA deprotonates the alpha hydrogen, forming the enolate anion here. It's a completion. Irreversible, single-headed arrow. It could attack electrophile like this aldehyde here, and then everything else is the same that we did previously. This is Aldol reaction here without the dehydration step.
So if we were to dehydrate it,
Yeah, if we were to dehydrate it, what would it look like?
would it just be our OH would be gone and then we'd have where would we have the alkene? At the
What?
1,4? Yeah, 1,4. So
Yeah,
1, 2,
like
3, 4. Okay.
Yeah. And this is our enone.
Perfect.
That's for dehydration.
Okay.
Crossed enolate for ketones with two sets of non-equivalent regioselective is a high degree of regioselective exists, and that depends on experimental conditions. So this is like lab stuff. You have to determine
Like
which one is major
thermodynamic.
and which is minor through experiments, and you determine that through like spectroscopy, NMR, and other filtration techniques.
Yeah, he barely talked about that part, so
Yeah.
slight excess of base.
Oh, okay. So this is going into elimination right here. Like E2 reaction, kinda. You see how here LDA is a bulky base.
Yes.
It can only go for the most available hydrogen. So let me draw out the hydrogens here.
Did you
Hydrogen.
say most available?
Yeah, the one that has the most free space. That's not bulky.
Okay.
You see how here these two hydrogens have like more space than this alpha hydrogen? It's gonna grab this alpha hydrogen and then make a double bond right here, which is why this is 99%, because this is the most free alpha hydrogens. Because think of the LDA as very bulky. Like let me say
So LDA is just used to make a nucleophile mostly.
Yeah, alpha nucleophile mostly, or double bond for E2 or E2 reactions.
Mhm.
You see how here this is a very bulky base.
Yeah.
This bulky base would prefer, I mean, any type of base would prefer to grab this hydrogen and form the more stable double bond because it's like more substituted. But in this case, it will actually go for the other hydrogens because it's more free. Like there's more like space around it.
Mhm.
But even though it's less stable than this double bond because there's less substituted, like less substitutions, this is the major product because of the bulky base here.
Wait,
And
why
this is like,
doesn't it make the double bond on the other carbon so that it's enone?
oh, this carbon over here. Oh, wait,
No,
this hydrogen here, because this hydrogen is
the other
less.
side, the left side.
Oh, this one.
Yeah,
Oh, and I make it enone right here.
yeah, right there.
It can't do that because if it does that, it's gonna this carbon is gonna have 5 bonds, because that carbon already has 2 hydrogens, like that. And then if we make an enone like that, then this carbon will have 5 bonds.
Yeah, doesn't it deprotonate?
Deprotonate, like,
Oh, whoa, wait. Oh, wait. 2,
I
4,
think when you have
6.
like another ketone.
are you talking about these hydrogens over here?
Oh, yeah, yeah, yeah. I see what
Uh,
you're trying to do.
yeah, these ones are less acidic than these ones.
So that's gonna be 10. And then the other one on the right side, that metal sticking out is also gonna be 10, right?
Yeah. And the reason why we take these alpha hydrogens instead of this, because it has more space, less sterically hindered.
Wait, is it 10 on that metal?
This metal here,
Yeah,
10 what?
10 electrons. So if you deprotonate that hydrogen and then make a double bond to make a enone,
1, 2, 3, 4, 5, 10 electrons.
no, like if you deprotonate the purple hydrogen that's already there.
Oh yeah, if you deprotonate it and make a double bond right here.
Yeah. 2, 4, 6, 8.
1, 2, 3, 4, 5. 5 bonds,
Oh,
10
yeah, the
electrons
other carbon.
of the hydrogens. And also this other carbon here. Oh no, the hydrogen got deprotonated. Yeah. This carbon would be fine, but this carbon would not be fine.
Yeah, I was thinking about the ring carbon.
Yeah, that ring carbon would be fine, but not this carbon. Okay. Does this make sense, Yvette?
Yes.
Okay.
Okay.
And if you have excess of the ketone, right, then your major product would actually be the more stable double bond.
Why?
Because think of it like you have less base. That less base will, let's see, when two earlier in the conditions, the ketone slight excess the more sensitivity. Okay. So let's look at the other case, the one where LDA is in excess. So if LDA is in excess, there's a lot of bulky bases around each other with competition. So they can't grab this hydrogen that they want to form the more stable double bond. So
Mhm.
they have to go for the more available hydrogens, forming this less stable, less substituted enolate ion. But if there's less LDA, then there's less competition to get this preferred alpha hydrogen and get our more stable substituted enolate ion.
Mhm.
And that's if the ketone is in excess.
Okay, that makes sense.
Yeah. And then all these are concept stuff.
Yeah, that I could just read.
Yeah.
Okay, that makes a lot more sense.
Mhm.
Like it's fairly similar, just slightly different steps.
Yeah.
I definitely am gonna go more over the micro reaction. I think that's where you lost me.
Oh, the microreaction stuff?
Yeah, but I think like just because I went over a bunch of practice problems with everything else, I felt more comfortable going over. And then I barely went over Michael, but it's basically the same thing as everything else, just a combination.
Yeah, yeah. It basically is, yeah, a combination and different type of nucleophiles. Like, is it ester? Is it ketone? Is it aldehyde?
Mhm.
And what type of electrophile is it? Is it enone? Is it a carbonyl? But everything is the same principles, like same pattern.
Yeah, and I
Yeah.
think you did a great job of like
Thank-
addressing the patterns.
yeah, thank you, thank you. Just do more practice, and then the micro reactions will click.
I feel good. I think I'm like more prepared now.
Hmm. Yeah, that's good. That's good.
Because I think the biggest thing I was having trouble with was making sure I had that extra bond.
Yeah, and then to address that problem, you do the start and dot technique.
Yes.
Yeah.
And then yeah, I don't feel uncomfortable with this.
That's
But
good.
yeah, we're still working on chapter 20, that's dienes and stuff.
Hmm.